In this video we will see the finite subgroup test. So far we have seen two subgroup tests. One is two-step subgroup test, another is one-step subgroup test. Let us quickly recall all those things we have learned so far. What is a group? A set with one binary operation. That binary operation says how to combine any two elements of that set. And if the set with that binary operation satisfies four axioms of group, that is closure, associativity, existence of identity and existence of inverse of every element of that set, then that set under that operation forms a group. What is a subgroup? A set alone can't be a subgroup. A set is a subgroup of a group, and that set have to be subset of that group first. So a set will be a subgroup of one group if that set is a subset of that group, first condition. Then under the operation of the group, it will satisfy all four group axioms. So a set will be a subgroup of one group if that set under the operation of the group is a group on its own. So that is a subgroup. And we have seen two-step subgroup test, one-step subgroup test. Those subgroup tests actually reduces our work. We don't have to show all four group axioms. A set will be a subgroup of one group if it will satisfy fewer properties. We don't have to show all four group axioms. And we have another subgroup test which will reduce our work further, and this is a subgroup test for finite sets, and this is called as finite subgroup test. Finite subgroup test, and the statement says let H be a non-empty finite subset of a group. Name of the group is G. If the condition is if H is closed under the operation of G, under the operation of group G, that is for any two elements of this set H, its product lies in the set also. If this is the only condition, then H is a subgroup of group G. So this is our finite subgroup test. We have seen two-step subgroup test. Two-step subgroup test says if any subset of a group has two properties is, first one is that set must be closed, and second one is set must have inverse of every element. Here we have only closed property, and set is finite. We will see if this finiteness forces the set to have the second property, then we will have this set is a subgroup of the group. So basically we will use two-step subgroup test because we have first step here already. We only have to show the second step with the use of finiteness of the subset. So let me write what we have been given first. Given H is a subset of group G, H is non-empty and H is finite. Also we have for any two elements, and we have for any two elements of the set H, their product also belongs to the subset H. We have to show what? To show H is a subgroup of group G. And we will use the subgroup test, two-step subgroup test. We will use two-step subgroup test, and by two-step subgroup test we have to show the set is closed and the set have inverse of every element. We already have the set H is closed under the operation of group G. So we only have to show the inverse part. So we only have to show for any element of the set H, its inverse also belongs to the subset H. We only have to show this one. And the finiteness of the set will help us to showing this property. So we'll show the every element of the subset H has inverse, and two-step subgroup test has also the non-empty part. H should be non-empty, and we have H is non-empty here. So we will only show every element of the subset H has inverse. Let us take element for A in the subset H. A equals to identity is the identity of G. If A is the identity and A is in the set H, its inverse is itself. A inverse is same E, and we are done. We don't have to check for the identity element which belongs to the subset H. If A is not identity, I think we are clear this point. A is an element of subset H. A can be identity and A can be other element. If A is the identity, we have taken A from the subset H. If A is the identity, its inverse is itself. So A lies in the subset H means its inverse also lies in the subset H. So we are done for the element identity. If A is not identity, let us see the elements. The elements A square. A square means A is operated with itself. A two times. A cube. With associativity, we can write this A cube. We have A, and no need to put parenthesis. Similarly, A4, A5, A operated with itself 4 times, A operated with it 5 times, and so on. All this belongs to the subset H. So for any non-identity element, we have A and its square, its cube, its to the power 4, to the power 5, all belongs to the subset H. And this is by the closure property of H. Because H has the closure property. Let's say take any two elements, operate them. The product you will get, that will be in our set. So the product A square is also in this, and this product A cube is also in the subset H, and all these elements belong to the subset H. Also we have this set is finite. Since H is finite, Finite means it has finitely many elements. It has, you can count the elements of the subset H. The elements can't go on like this set of integers or the set of natural numbers. We have finitely many elements. We can count them. We have either 10 elements, 100 or 1000 or 521 elements. Here we have infinitely many things, isn't it? We have powers of every natural number. 5, 6, 7, 8, 1000, all those powers. These are infinitely many. And if these infinitely many symbols or the elements belongs to the subset H and H is finite, so what happens? They must repeat themselves, isn't it? If they all are different, then we will get a contradiction. Since H is finite, the elements a square, a cube, a to the power 4 and so on can't all be distinct. So they must repeat themselves. So if they are not distinct all, then for some, then for some natural number I, natural number j, and I not equals to j, we can have ai equals to a. Since all these are not distinct, we will have some power of a is equal to some other power of a. So we will have this condition for some I j and I not equals to j. I can be either bigger than j or I can be less than j because I is not equals to j. Say I is bigger than j. For I less than j, we will also have the same logic. Say I bigger than j. So what we have? I number of a's here. We have a I times which is equals to a j times a. Let us operate the inverse of a j times on both sides. We have a I times and I am operating a inverse j times. In the right side I will have a j times a. It is understood. I am operating a inverse j times. We have a j times a inverse j times. So I will get identity in the right side because by associativity we can have a inverse, they will operate with themselves to give identity. This I is bigger than this j. This a and this a inverse will operate with themselves to give identity. Identity with a inverse is a inverse, and we have also a here, and this a with a inverse will give identity. So in this way, j times a, j number of a will be cancelled with a inverse j times a. So I will have how many a's here? I will have I minus j a, because total I have I number of a and j number of a's are cancelled with the j number of a inverses. I minus j number of a here. So in the right side we have identity and in the left side we have, and note a not equals to identity we have not taken first. A is not equals to. That implies this I minus j can't be 1. This is bigger than 1. I is bigger than j. So I minus j is positive, a positive natural number, 1, 2, 3 or 4. But it can't be 1 because a is not same as identity. If I minus j is bigger than 1, then what is I minus j minus 1? This is bigger than or equals to 1. This is bigger than 1, this will be 2, 3, 4 and so on. And if I will subtract 1, I will get 1, 2, 3 and so on. So this I minus j minus 1 is bigger than or equals to 1. And what is this one? A times a to the power I minus j minus 1. Here we have 1a and they will sum up to give a to the power I minus j. This is a to the power I minus j. And in the right side we have identity. So if a is operated with this element, then we will have identity. That implies inverse of a is a to the power I minus j minus 1. But we are not done yet. We have found the inverse of a. But this element should be belong to the subset H. And we have seen a, the powers of a, that is powers of a square, a cube, all these powers belongs to the subset H. And this is also a power of a. That implies a to the power I minus j minus 1 also belongs to the subset H. And this happens for every element A which is not identity, and for identity we have already shown. So for any element of the subset H, we will have its inverse also in the subset H. Hence we are done and we are happy. And this is the finite subgroup test, and this is only applicable to the subsets which are finite.